Thank you all for being here. It's a pleasure. Thank you, Adriana and Sabine, for the introduction. That was very nice. Actually, I was just informed that since I'm in two faculty, I have to give two speeches, so it's going to be long. It's a joke. I'll probably have to explain to you why I call the talk Carrying the Torch for two reasons. First, because I'm still active within EPFL with EcoCloud. And second, and more importantly, because as an educator, as a professor, you really never stop doing the work that you like. That goes on with your life, and that keeps you busy. We're in Lausanne, the city where is the siege of the Olympic Committee. And the values of the Olympics are very important for all of us because there is a similarity to the values that we have in education and in research. The values of Citius, Fortius, Altius, and Communiter. That is, faster, stronger, higher, and within the community. Note that the last word was added about 5 years ago by the Olympic Committee to the motto. And that's important because that's a shared value. These are shared values within our community as well. Next, the picture. That's important. That's Muhammad Ali lighting the Olympic chaudron, the chaudron, in Atlanta in 1996. That was an important moment for various reasons. Muhammad Ali represents diversity. He represents resilience. He was stripped out of his titles because he refused to fight in the Vietnam War. He came back after when they canceled his conviction, and he fought again. And lastly, and most importantly, in 1996, he had Parkinson and was very sick, but he still made it to go there, carry the torch, and light the flame. So that's important. And the next important thing is the torch itself. The torch represents the message that we carry around. And the message goes in both directions. We teach students, and we learn from students. We spread ideas to colleagues, and we learn from them. That's a movement that goes in both directions. That is extremely important. So the torch is the message, and the ring, the circles, we'll see many circles in these talks that represent the community, that it's important. For those of you who are fans of skiing, here you can see Alberto Tomba and Deborah Compagnoni. They were lighting the Olympic flame in Milano in February this year. And that's under the Arco della Pace, the Arch of Peace, near Corso Sempione, actually a couple of kilometers from where I grew up. Milano is my hometown. And the sphere holding the flame, it's a connection of circles connected by knots. These knots were originally designed by Leonardo da Vinci many years ago and used for the flame. So again, the concept of this talk is looking at the circularity of information to the community. I dedicate this talk to you, to the scientific community, to the teaching community that's around me. So that's where it all started. Again, the community. This was one of the NATO schools. This is 1980. I'm there. I don't know if you can recognize me with very long hair. And I was there. That's where I met for the first time some of the leaders of the field. Later on, in '86, actually I was directing one of these NATO institutes. I'm there with a bunch of colleagues too. And this institute was about synthesis. I'll talk more about what is synthesis of integrated circuits. And that's another picture of the community. There was kind of a planet alignment in 2018, and most of my graduate students were there in the Bay Area, and so we gathered together at Stanford, courtesy of Professor Subhashish Mitra, and we had a wonderful reunion. So again, that's the community. But in my talk, I will also get into what I've been doing, not chip design, What are these chips? You know, many of the wonderful applications that we use today, from telephones to smart cars, are actually based on silicon chips, how you design them. So we have to look at the inside. And this actually is the insider view of how a chip is done. So this is somebody who lived very close to us in Vevey. And he was not an engineer, but this picture captures a lot how an engineer can creep through the various parts of a system. So I was mentioning synthesis before, and part of this work originated during my stay at IBM at the T.J. Watson lab in New York. The idea was to be able to design a circuit for a program. That is synthesis, getting a high-level description of a circuit in a language and map it into the description that is ready for manufacturing. That's what is called the layout of a silicon chip. Well, of course, at that time, that was considered a little bit of a crazy idea. Designers at IBM were telling me, you know, the program is for software. You're doing hardware. Hardware, you do it with a schematic. But now nobody uses a schematic anymore. Everybody uses synthesis technology, mapping high-level descriptions into the layout of a circuit automatically. And by the way, this is an 801 processor. This was a RISC architecture. This is what actually influenced later on the RISC processors at Berkeley, at Stanford, and so on. And that's the team. That's the team, the community that worked with me on the Yorktown Silicon compiler. We took this picture when I just left at Stanford. And, well, there's one person there to the right that didn't write a single line of code. That's my spouse, Marie-Madeleine, but she's been extremely influential and supportive during all the years of research. And that's why we always like to have her with us. And that's the team 30 years later. This is the honorary lecture of Ralph Otten, who is sitting in the middle, and we all took the same position, and we turned the head in the same way. As you can see from the picture, we all got much wiser through the years. But that's not the important thing. The important thing is actually looking at the growth of the importance of the semiconductor market, not just due to us alone, but we were part of the puzzle. And the semiconductor market grew tremendously between 1986 and later on, 30 years after 2016. And then there was a time in which I was at Stanford. And that's me with the mustache. And I was very fortunate to be in this great institution and then being part of the Center for Integrated Systems. The idea of this center was extremely powerful because it was bringing together people from various technical communities. I had as neighbor Jim Plummer, who is a technologist, and John Hennessy, who is a computer architect. And we all were getting together quite often for meals and discussing and actually crossbreeding ideas. Also, the center was open, of course, to students, but to the community in Silicon Valley and reaching out also to external communities, so creating bridges from the community, from the academic community outwards. And was part of this outreach that actually was fortunate enough to be able to go to the Stanford campus in Kyoto and working together with the colleagues of Kyoto University. That's me on a bike in Kyoto. And that was not an easy proposition because keep in mind that in the 80s there was quite a big animosity between the United States and Japan. Japan was supposed to take over the world with computers and with AI, but it was probably a little bit too early for the times. But the experience at Kyoto was extremely useful for me and was also important to meet the local community. One of the efforts there for community building was basically led by Bob Dutton, professor at Stanford, and Tosh Aquino-san was director within Panasonic. The idea was create a working group between Americans, some Europeans, and Japanese to share ideas to look at the problem of design that was typically taken from different angles to see what were the common denominators, what were the points in which we could do research together, the way in which we could communicate. And this was extremely instrumental to the growth of both the technology and also to the international understanding, because a lot of the community service work is extremely useful to make people understand that we can be different, but in the end we have the same problems. We talk about the same language. And as part of this effort of going to Japan, I took 2 students with me that came along, and this picture was taken at Panasonic. It's 1992. These are Dave File and Jerry Yang, and while being in Japan, they figure out that, again, a way of bridging cultures, bridging different problems, relate to create some sort of a classification of knowledge, an ontology, as it's called. And Japan was the time of incubating a project. The project was Yahoo. Yahoo as a company was developed on a computer called Akebono. Akebono is a famous sumo fighter. He's not Japanese, he's American, he's the only American one. He passed away short ago. But Akebono was a computer, is a computer. I still have the computer in my cellar. And it's still running. And it is where they developed Yahoo, that then became a corporation and actually marked the world because it was one of the first actually global internet company. And it came out of the experience in Japan. Now, let me go back to Stanford and chip design. This is a revealing picture. This is Pete Mondrian, and this picture actually was painted in 42, I believe, as I've written. And it resembles quite a bit the layout of an integrated circuit. He had no clue of what an integrated circuit was, clearly, at that time. But you can see blocks, you can see connections, you can see contacts, you can see vias in here. It was just imagination. But I use this because during the work at Stanford, one of the major issues that we were confronted with was the communication among blocks, the speed and how you can make practical the connections. And indeed, in integrated circuit, it is all about smart connection if you want to have a circuit that's performing and fast and using little energy. And that's where the concept of network on chip came by. And it came by from Luca, who is sitting here, and actually realized my dream to have a student who is much better than me, but he is still a student. And Srini, who actually was my last graduate from Stanford, and who's here in Lausanne. He is an entrepreneur. And Federico, who's here in the audience, and Antonio, and they all contributed to making this idea of network on chip into a set of tools in a company called Inox that was later acquired by Arteris. And that's a picture of Charlie Janak, a serial entrepreneur, extremely successful, who saw the light of the network on chip, actually, who acquired the technology and who's making actually the only company who sells worldwide network on chip technology. Just one more slide, taken from Federico, I believe, to tell you what is this important concept of a network on chip. You have various elements on a chip, and you want to connect them. It's complicated. How you do it? More or less like on the internet. You have routers, you have links, and then you have the communication that can be handled in a structured way. Now what's important is that NOC, network on chips, are used virtually in all electronic products. They may be using different names, different flavors, but they are networks on chip. This technology is used all over and makes the design scalable. That's how we can get to chips that have billions of transistors. And then these NOCs are critical again because we want in chips to have the best performance with the smallest energy consumption. Back to EPFL, back to having fun The reason why I have this job is because I'm having fun in doing research. That's the only reason. And part of the fun was discovering also the device side of things, looking at transistors and how you can innovate in doing transistors. Transistors are switches that can be open or closed according to a value that can be true or false. But there are two types of transistor, the P or the N, and they're complementary. But you can make one single transistor that does both functions. This is called a polarity control transistor. That's a sketch of one of them. And I've seen Thomas before, and they had at LETI the glorious name. This is a hermopolar transistor. Hermopolar, means herma could be either gender. The gender can be decided after design by just putting a signal on it. So that actually brings programmability into the devices. And I need to acknowledge that this work was done together with Professor Leblebici, who is now at Sabanci University as president, and Pierre-Emmanuel Gaillardon, who was one of my postdocs, and now he is professor at University of Utah in Salt Lake City. And that's a picture from the fab. It's great at the EPFL to have a fab where you can try out new things, new devices. This is a realization of a gate array with this type of devices. Looks nice, but keep in mind that I'm cheating here. Silicon is gray or silver. You can actually look at it. It's extremely boring to look at a picture of silicon. But there's a tool which is important in your life, which is actually being able to do, coloring pictures. And this has been actually colored with a tool so that you can see the green for the wires and the purple and blue for the transistors. But what happened next? We had these new experimental devices. How do you design them? What do you do with them? So what you can do is to come up with circuits that are fairly compact that use these transistors. And they basically use exclusive OR. Exclusive OR means an either-or condition, and majority gates. Majority are gates that will be true if a majority of inputs are true. And this brings a new way of thinking about how you do design. But then you need to find tools to design with these gates, because typically tools look at implementations that use gates that are different. And this work was done with Matthias Söken, who is now with Microsoft, and he's around here, and Heinz Riener, who is now with Cadence in Munich. So the idea was to exploit a new design paradigm that can leverage this type of gates. Again, that's majority. I gave this talk in Washington, D.C. in 2020. And I think it was successful. I should have given it again in 2024. It was a major loss. Majority is one of the key values in electronics and in society. But more than that, I found this citation in one of the books of Donald Knuth, the good Donald, The Art of Computer Programming, one of the latest volumes, the 4A, in which he shows that not only he knows software, but he knows also everything about hardware. And Donald says majority is probably the most important operation in the entire universe, because there are operations that are continuously discovered and rediscovered. Out of this, what I like the most is the rediscovered. Because majority existed in the 60s. People used that to design adders and multipliers, but there was no systematic way of designing large-scale circuits using majority. And now, majority is used for CMOS design, majority logic synthesis based, which actually brings up a concept which is important and I'd like to convey to you, which is the notion of the innovation ring. We see another circle, another ring. So we started by using the run-of-the-mill technology, which is CMOS, which everybody is using. Then what we did this new type of devices, this new technology with these new gates that I showed just before. Then we needed what? We needed design tools and design methods for this new technology. But we couldn't measure how good it was because the technology is an emerging technology. So we needed to test these methods on CMOS. And then we discovered that these methods, based on majority, actually do very well on CMOS, and actually you can improve circuit speed by about 20% using technologies, logic synthesis, that exploits majority logic. So this type of design technology is now used by commercial vendors and, of course, by academic sites to design CMOS circuits on an established technology. And, of course, it's extremely important for emerging technologies. Some more fun. When I came to EPFL, I like to take advantage of everything, so I like to do something in a wet lab. And at some point, I went to Willy, and I told him, Willy, I would like to have a wet lab. And Willy looked at me. He said, well, there might be space in the base of IMM. And then I told him, well, we need to know where we're going to put the bottles with the gases. At that time, Willy said, no, this is not going to happen in INC. But I was lucky enough that I also had another dean, and so I could find some other space. This is a little bit like being Hermapolaire, you have two sides, and you can enjoy both, and so I found another space to have a wet lab, and having fun in fabricating and testing. Here we were testing biochips, and that's work done together with Sandro Carrara, something that I enjoyed a lot, and this is an example of sensors. There's a sensor part, which is coupled, of course, to the electronic circuit design, and this is used to sense some metabolites in the bloodstream. This is another small chip that was designed. It's a system-on-chip that has 4 sensors on the top, and it could be implanted in an animal model, and the poor mouse could run around in the cage and still be monitored with radio frequency and with just a detection and monitoring system. So that was a lot of fun. It was also discovering a new world that led me to the idea that we can apply electronics and computer science to a universe that's much bigger. And led me the idea of creating this program, Nanotera, that aims at applying electronics and computer science to health and the environmental domains. And this was started as being a project, then it became so big that it became a program, a federal program run directly by the CERA, not by the National Science Foundation, as I'd like to say. But it was an experimental program that was a little bit out of the typical mindset in Switzerland, but it aimed at gathering people on collaborative project. Again, the notion of community, of collaboration was extremely important. Bringing together people with different backgrounds from different institutions, finding out that people from Lausanne and Zurich like each other when they can share the research and the money. And not only these two cities, but everybody kind of in Switzerland enjoyed that. So Nanotera means that we want to research design systems that are large scale, tera scale, using tiny devices, nanoscale devices. And examples are, for example, been monitoring the permafrost and the rock movement in the alpine setting. This was research done in collaboration, and the leader was Lothar Thiele from Zurich. This picture was part of a very interesting trip that we did on the top of the Matt Valley. I liked so much the trip, and I decided I should never drive on the road below because how much the rocks move. This is an autonomous robot swimming in the lake. This was Iceberg project. Again, it was a collaboration project between EPFL, Zurich, and other partners. And the robot can swim and look for pollutants and disturb minimally the lake or the river and get samples. And this is a an ultrasound design. I see Aya there, who actually participated in the program. Again, was a collaboration between us at EPFL and Zurich. Again, Luca is there. And you can see on the left the board that was doing the computation, on the right the probe. The idea was to having a device which is a portable 3D ultrasound device that you can use in emergency to check what is the injury of a person and then transmit the image, which is a 3D image that can be measured far away. So all these things brought me a lot of fun, and EPFL for me has been a great experience because not only I could do research, but I could taste various flavors of the research and working together with wonderful people. In the next part of my talk, I would like to mention a vision for the future, what I see coming up, what are the issues. And I will start by this wonderful picture by Umberto Boccioni, 1911. This is the mother of the invention. Some of the paintings of Boccioni related to his mother. This is a woman that actually can see into a smart city. All the elements are there. The smart building, the smart communication, the idea that there is a future, even in 1911, that can make our life better. Unfortunately, part of the vision of Boccioni was ruined by World War I, that destroyed many of the ideas that were there at the beginning of the century, and that killed Boccioni, who died in the war in 1916. But the lesson still says, and part of the lesson is that realizing complex systems requires a multitude of skills, and you have to leverage the human capital. Creation is mainly done by humans. At the same time, dominating societies need to be rich in culture and knowledge, because you need to bridge between engineering and humanities in order to see things. And so for us as educators, broad education is key to technology growth. You cannot just teach engineering. You have to look around and look what is in society, what is in art, what is in literature. And diversity. Diversity is important. Diversity is a search of richness because it brings many ideas, many ways of behaving, of being to the table. Education. This picture actually, it's Raffaello's Schools of Athens. It's a classic. Well, we teach to educate engineers, scientists, and leaders. Remember that some heads of states are engineers. And we want them to be able to enhance, correct, and govern a complex society. A society, in the end, is a complex system, and we deal with fairly simple systems. So actually, the roots are there when we educate people. We have to look at what is the possible future. And we want to use all possible advanced technologies. And in this, of course, I mentioned the use of AI. I'm not too much about AI because everybody talks about AI. I'm not an expert on AI. But we have to use all this technology while being risk aware. That's the important thing because we have to keep the human in the command room no matter what we are using. And then we have to use an ethical reward function, like a good colleague of mine, Moshe Vardi, mentioned in a recent article on ICM communication. If you look at how you can employ different AI systems, are they good, are they bad? Well, it all depends what is the aim that you have. You want to do things better or you just want to do money? And so I will put a quote which I like very much that comes from Bertolt Brecht's play, The Life of Galilei, Lebens des Galilei, that says that the only purpose of science is to ease the hardship of human existence. And I think that's something that have to have us reflect a lot. Science. A vision for science. Not long time ago, I was looking for my books. It came across Chance and Necessity by Jacques Monod. Jacques Monod was a biologist, received the Nobel Prize, but he wrote this book much later in time, and his claim that everything happens by chance. In our settings, in our type of research, I would say that advances may happen by chance. Sometimes it's a conversation, sometimes it's an idea. There are many sparks that sometimes lead to new products, to new developments. But it's not just the accident itself. We need to create the necessary environment. So as a research leader, what I try to do in my work and in my group, in the community, is to create the conditions by which sparks that maybe come out of accidents can actually create a flame. This is extremely important for us. Otherwise, the sparks actually may just go away. Where we are living a type of multiverse where there is not a single solution to problems. When you look at engineering problems, when they succeed or not succeed, it's just because there is a superposition of technology, economics, and politics in most of the systems that we design. And we have to be aware that that's what happens. And we have to look at all the various angles of the picture. But we, as educators, we need to provide directions in uncertain times. And I think that we are living through very uncertain times in terms of ideology, in terms of stability of the planet. And our generation is responsible toward the younger one. We need actually to make sure that we can maintain peace and democracy. We can save the environment. Especially as educators, we need to infuse faith in the younger generation that there's a better future in front of us. And that we, with them, we have to fight for this better future. Being positive all the time. That's important. I have dreams. I had dreams. Part of my dreams about the future, and I will start from this chip, Basilisk, that comes from Zurich. It's again, Luca is responsible for that. It's a chip that's been designed with open source tools. Open science is extremely important for all of us. When you look at computing, when I think of the future, it has to be accessible and secure. And it has to be able to be designed with open source platforms so that we know what's inside. It's our right to know what's inside everything that we design. When you look at social services and networks, they have to be multicultural and freely available. And actually, I'm very glad that the Apertus initiative in Switzerland, it's a wonderful initiative for AI, and it's along these lines. But we have to remember that we also have to provide the last mile connection. We have to make technology available to disabled people, to junior people, to elderly, and very often we forget that there is this life connection, which is very important in a democratic society. And of course, energy sources. Energy sources are important because they have to be diverse, they have to be carbon-free, and it's very important to have a circular energy economy in all dimensions. By this dimension also I intend nuclear energy and circular nuclear energy where there are no debris, where the debris are recycled. And that is possible, it's been shown to be possible, except that it's expensive. So if we want to save the planet and consume less CO2, we have to be ready to pay the price tag for that. Talking about power, again, my dream. How to power computation. We need a balancing act, because on one hand, we have the rapid increase of AI and the share of energy that AI is taking. And at the same time, we have this growth of the temperature of the globe that's getting beyond control, beyond the 2 degrees raise that was supposed to be controlled before 2050. How do you handle that? You have to handle that through a combination of techniques. But what is important if you look in the future, computing is just an engine, and thermodynamics actually governs most of it. Finding out ways of overcoming the roadblocks for AI with methods to reduce and recycle the energy that it's used to feed the computers as well, which is dissipated within the computer. And that's one of the goals of the EcoCloud Center, which I have the honor to direct here at the EPFL. I had a dream. This picture shows Konosuke Matsushita. He was the founder of Panasonic. And his motto was, peace and happiness through prosperity. Have money, you buy all kinds of electronic gadgets, your life is going to be much simpler, much happier. And this was taken by other people who changed the words into peace and progress through prosperity. This is a motto which has been often said, and it came actually from the original words of Matsushita himself. The three concepts are, of course, strongly related. Here you have another circle of cause and effects among the three P's. But I like to do a small permutation. I like to say progress through peace and prosperity. We are here, we want to have progress in society. We need to maintain peace, we need to maintain prosperity, where in this case prosperity means funding to institutions. I think we all agree on that. But that's extremely important if we want to have progress. So I will summarize this notion of this ring. Again, this is Matisse Ladin's very famous picture. You know, it's very important, the community itself, the circular interaction among people, the possible migration of human and ideas on the Earth's surfaces. There are many ideas. There are more than 10 million ideas in the world that could be useful. 10 million is not the limit. The other important thing is the crossbreeding of technology, science and humanities. You know, broad education, it's important because broad education enables these sparks of new concepts. And third point is circular energy schemes are extremely important to power up computing. The circle, the ring. What is the best picture here? Alain, you were the one taking the picture. This is one of the nicest pictures of EPFL that I like. It's the Rolex Center under snow. And you can see this disc made of snow. And if you're careful and look at the borders, you see kind of the diffraction patterns of the flakes of snow coming down through the Rolex Center. Beautiful image. The arches. These are the arches of my life. Starting from Milano, the Arco della Pace, the Arch of Peace. The arches of Stanford University while looking out of Memorial Church. The arch of the Rolex Center here in Lausanne. There's a symbol behind the arch. The arch expresses the joint effort to achieve a challenging goal, which is keeping the weight up, working together. So at this point, I need to say a few words of thanks, starting from Berkeley, from my advisor, Alberto San Giovanni, Richard Newton, Bob Brayton. With Bob, we wrote until he lived. We wrote the last paper together about 2 years ago, maybe still in the queue and not published yet. But it was a great pleasure to work with all of them. And Stanford, Bob Dutton, John Hennessy, Ed McCluskey, they have been not only mentors, they taught me how to do research, how to lead a group, how to progress. Now the embarrassing part. It's very difficult to thank people at the EPFL because there are too many. And if I make a list, I will probably forget somebody. So I will just stick to two. Daniel Manch, with whom we had lots of discussion about logic, and he brought me to EPFL on a sabbatical, and then Lausanne EPFL became addictive, and we ended up staying here. And Patrick Ebischer, who hired me, and I would like to thank Patrick for never masking out the interrupts. That's a medical doctor who understood computer science. I'd like to thank my colleagues. I have this picture of the retreat of INC in Diableret. Very nice place where we had a lot of discussion. But there was a particular highlight at the meeting, which is the snowball fight happening after the dinner. And so I think that you will see me going to this meeting, or at least being there for the dinner and the after-dinner fight. I don't have a similar fun picture about SDI, but would like to thank all colleagues of SDI for their fellowship, their friendship, and their support. I would like to thank people who worked with my lab, within the lab or outside the lab, Pierre-Emmanuel Gallardon, now professor in Utah, Sandro Carrara, professor at EPFL, Yusuf Leblebici, who is president at Sabanci, Matthias Soken at Microsoft, Hans Riener at Cadence, and Vasilis Pavlidis, who is now professor at Thessaloniki University. I would like to thank my graduate students. Without them, the research would have never been done. So that's extremely important. I would like to thank the people who work as staff in my lab, Christina, Carol, Chantal, and Chantal. There were two Chantals. I would like to thank all the staff at EPFL, Suzanne, Philippe Guébanma, who was an incredible resource for me in running the Institute of Electrical Engineering, and really all the staff around the units. What was fantastic for me at EPFL was the level of support much higher as compared to Stanford, which enabled me to spend more time in doing what I like, that is basically research and teaching. This is actually an incredible value that's there at EPFL. I would like to thank my colleagues in research and science. I ran a few conferences in Montreux. This is the last one that we had in 2023. We were up there at the restaurant Cuckoo, and everybody actually enjoyed the fun spent together as well as the discussion of ideas among us. And last but not least, I would like to thank my family for never stop exploring. So this is Marie-Madeleine with me on a kayak in the Arctic a few years ago. And this is again Marie-Madeleine in the desert in front of the Hormuz Strait in February, just a few days before the mess started, but she's looking east, quite happy. And the sky was blue and not disturbed by you know what. That's with my son Andrea, when we crossed over into China, and we wanted to go to China by land, not by air, not by water. And so we crossed over by Kyrgyzstan across the mountains. The Chinese didn't believe it, but at the border there was a gate. There was a gate with a padlock, and after checking the visa, somebody opened the gate, and we could pass on the other side. And that's my daughter, Gabrielle. A couple of years ago, we were on the Andes climbing, and we were up on the mountains and actually looking at the blue sky over the ice, and it was a great experience. And I would like to thank all of you for being here today and sharing this with me. I would like to thank my sponsors who actually enabled me to do research. And I'll close with a picture of rings by a contemporary artist, Lorenza Morandotti, who's also a very good friend of mine in Milan. Thank you so much.
Thank you, Sabine. So I'm here for the formal part. So it's a formal event for Nani, so who has a tie. And I figured I'd have a tie too. So there's at least two of us, but I saw Andrea has a tie, so there's three of us. There's a few of us who will share stories from the Stanford days in the room that I recognized. If my math is correct from Sabine's mathematics and explanation of Nani's bio, you had been a professor for 8 years at Stanford when I arrived, but I was smart enough not to take the qual with you. Now, a number of you are here because as colleagues of Nani, and of course, we all know how much he has influenced all of us as colleagues. A large number of you are here because you owe a significant fraction of your career to Nani because you were his students. And I actually am one of the people who also owe part of my career to you, because there's actually 3 people that are the reason that I'm at EPFL, and they're all 3 in the room, so I'll mention it. Martin hired me, but he hired me after I had talked to Willie, and Willie said, well, I used to be the dean, but I'm not the dean anymore, so talk to the new dean, and the new dean was Martin. But before that, we have a common friend, which is Silvano Guy, and I was thinking about going back to Europe, didn't exactly know what to do. I was still at Cisco. I was kind of miserable at Cisco. Silvano was miserable at Cisco as well. And he said, well, if you're thinking about Switzerland, you should talk to Nani. And remember, probably don't remember, we talked.
I remember.
And then 2 years later, I was at EPFL. So I think everyone here owes a debt of gratitude one way or another to Nani, and that's why we're here to celebrate. Now, for the formal part, I have to read something in French. That's the rule. It is the official EPFL degree, and we're an efficiently run organization. There is only one font for all the degree types. So you get your bachelor's degree, your master's degree, your PhD. It's the same font. You get to be Professeur Honorary, it's the same font. So I need to move here because I need to put my glasses on. So, and you will need to put your glasses on too to read this. It's not an age-appropriate font for Professeur Honoraire. Okay, so, are you ready? L'École polytechnique fédérale de Lausanne, sur proposition de la conférence du corps enseignant, décerne le titre de professeur honoraire à Monsieur le professeur Giovanni De Micheli, en reconnaissance pour ses contributions importantes et soutenues à la recherche dans le domaine de la conception de circuits intégrés, notamment en synthèse logique de haut niveau, virgule, en raison sur puce, virgule, en électronique de basse consommation, en gestion dynamique de l'énergie, en biocapteurs intégrés intelligents, point virgule, pour avoir inspiré, encadré et formé plusieurs générations d'étudiantes, d'étudiants et de doctorants, point virgule, pour avoir transféré des outils logiciels et des flux de conception à l'industrie de la conception électronique automatisée, point virgule, pour avoir créé et dirigé le programme fédéral Nanoterra, consacré à l'amélioration de la santé et à la surveillance de l'environnement, point virgule, et pour avoir dirigé l'Institut de génie électrique ainsi que les centres Integrated Systems et EcoCloud. Point. Félicitations.
Magnifique. Merci, Edouard.